Alright, hi Lavanya, I hope you can hear me. This video is for your self-study. I'll be covering three subjects: software engineering, computer networks 2, and system software and compiler design. Each subject will have three aspects. One related to green computing, maybe you can use that. How is it related to the topic? That's number two. And how you can use your packet generation tool to demonstrate topic or point number two. So let's get started. Uh, this applies to both software engineering and CN2. First aspect is green computing. Of course, you need to achieve greenness by software which is optimized and it has smart features such that it turns the light off as soon as you leave the room. Something as simple as that. Well, that can be used in software engineering. One aspect can be the requirements phase. I know you are not familiar with it, but before you start building software, one way you can reduce time as well as energy is by optimizing the requirements elicitation phase. You will learn more about it. I won't talk about it now because it's really boring. To give you an example, you can use the monosec server to detect a denial of service attack. For example, if a SYN flood is detected through your packet generator program, the actual web server goes into a sort of hibernation mode, and it only services requests which are limited in number and are not coming from the same list of hosts which are constantly and mindlessly sending SYN packets. So this adds to that green computing aspect by not trying to serve mindless requests. This can be used in both SE and CN2. SE, I'll give you details once you have studied it because you need to. To give you an example, you can see the all denial of service attacks go from the attackers, which is generally all over the world, to mostly America. For SS and CD, there are two splits for system software. System software must be highly optimized to realize green computing because system software also includes device drivers which run hardware. For a case study, you can use the Linux kernel itself because the Linux kernel contains inbuilt drivers which are system software which run devices on your computer like your video card or your sound card. Well, the drivers in the Linux 2.6 kernel gave you a peak temperature of 67 degrees centigrade, but by the time Linux upgraded to 3.2, despite the advancements in technology in 4 years' time, for some reason, mostly because of bugs and incompatibility, that same task used to raise the core temperatures up to 86 degrees centigrade. Now, associated with your packet generator tool, you used raw sockets or sock_raw. So basically, you created your own headers for all your packets. You took away the job of the kernel. So here, I think you can include another aspect where you compare the time taken to send a packet on the wire using raw sockets, that is your packet generator program, versus the time taken to send that same packet by the network device driver and plot graphs. Basically, you just use sock_stream and use the send function, that is to simulate the kernel making its own headers. In the second case, you use sock_raw and your pacgen program or the send_to function to create your own headers. You just plot the difference in time between these two approaches and you can see how system software needs to be computing. The second part is compiler design. You may agree with me that lesser the automata or smaller the automata, you get more green computing. Similarly, less complex the grammar, you get more green computing because there are less states to go through. More optimization in that grammar, for example, reducing the number of useless states or removing any terminal symbols, more green computing. Lesser states of the automata, that also means more optimization. To give you an example, first, example 1. I told you about stateful protocols, e.g. TCP. So you have the client and the server, you have syn plus ACK and ACK. You see that these are states. If you refer the Tannenbaum textbook, which has been prescribed in your syllabus, you will see that there is a state transition diagram for TCP connection establishment and TCP connection termination. This is the final state. So I'll put two rings here, and this is the penultimate state. So there is a definite pattern which needs to be followed. You see there are 6 states ideally, if you check it out. On the other hand, if you have stateless protocols, e.g. ARP, whatever input you give is the final state always. So if there is an input set I which contains just 1 minute, this is too annoying, A, B, C and so on, then for all I, small I belonging to capital I, whenever you perform this, you get the final state. So that is a stateless protocol. You can see that the final state is being reached in O of 1 time, correct? While you will take O of n time in the case of a stateful protocol, where n is the number of states. In stateless protocols, anything you give as input always goes to the final state, and the starting state is also the final state. So basically you take O of 1 time to achieve the same result in a stateless protocol. So to achieve green computing, stateless protocols are much more preferred. You can maybe give this example. Example 2, you may know that just 1 minute. Yeah, you know that there is a network, and this can be treated as a graph, right? Now, instead of treating these nodes as networks, these nodes in a network as nodes themselves, you can treat this entire graph to be a restrictive automata. I'll just show you an example. I'll leave the others for simplicity. Suppose you have a computer network which is connected like this. Alright. So if you have a computer network connected like this, and you need to send a packet from node 1 to node 2 here, you can see that only those nodes with a connection can be used to send a packet or transmission. So you start from here, you go here, and then you send the packet here. So you can see that these two edges were not needed. As a result, this little part of the network can be considered an automata, because this is the starting state and this is the final state. So if you move from state 1 to state 2 to state 3 to state 4 to the final state, state 5, you get an automata. So think about compiler design working that way. So I hope this helped you. Thank you so much for watching. If you have any doubts, let me know. That goes without saying.